Up next, we consider hypergeometric theory as we continue with the special functions playlist. And here we have a comprehensive study of hypergeometric differential equation, hypergeometric series, Gauss hypergeometric function, transformation formulas, analytic continuation, confluent hypergeometric functions, Kummer functions, Whittaker functions, and generalized hypergeometric functions. Let's go on. So the introduction now, um, hypergeometric functions are among the most important special functions in mathematics and physics because they arise naturally in differential equations, quantum mechanics, electromagnetic theory, geometry, mathematical physics, and statistics. Many classical special functions are many classical special functions are special cases of hypergeometric functions. So it means that most of the special functions we know, they are actually special cases of hypergeometric functions. So, and this includes things like exponential functions, trigonometric functions, Bessel functions, Legendre functions, Hermite functions, Laguerre functions. We've seen a lot of these kind of functions. So the word hypergeometric comes from the fact that the ratio of consecutive coefficients in the series expansion is a rational function of the summation index. That is where hypergeometric comes from. Now let's look at the power series. Let's review power series. We've seen power series in a couple of situations like Taylor series, Maclaurin series, and things like that. A power series centered at x equals 0, for instance, has the form summation from n equals 0 to infinity for an x raised power n. Now, if it wasn't centered at x equals 0, let's say it was centered at x equals c, it would have been a sub n, x minus c, all raised to power n. Okay, so in this case now the c is 0. So we have examples like the exponential function e raised power x. So we can write e raised power x as summation from n equals 0 to infinity for x raised power n all over n factorial. And for the sine function, we have sine x equals summation from n equals 0 to infinity minus 1 raised power n. Because sine is an odd function, then x raised power 2n plus 1 all over 2n plus 1 factorial. So that's a kind of a brief review of power series that we considered in earlier videos. Now, the Pochhammer symbol, which was the fourth video playlist, in this playlist rather, so the Pochhammer symbol, which is the rising factorial, can be defined as a sub n, which is a into a plus 1, a plus 2, up to a plus n minus 1, and with the fact that a sub 0 is 1. So, Pochhammer symbol gives us the possibility of expanding, of extending functions from a particular value instead of starting from 0, starting from 1, that we have in the case of factorial. For instance, if you have 7 factorial, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. But if you have 7 sub 3 in Pochhammer, that'll be 7. So it means that from 7, go 3 steps. So that's 7 multiplied by 7 plus 1, which is 8. That's 7 times 8 times 9. So from 7, 3 steps starting from 7. So 7 times 8 times 9 in that case. So, but A naught is equal to 1 in case you have to deal with that. For instance, we have 3 sub 4, that is 3 times 4 times 5 times 6. So starting from 3, goes 4 steps. 1, 2, 3, 4. Consecutive numbers multiply starting from the given number in bracket, and this is 360 in this case. It is also possible for fraction. So 1 over 2 sub 3, that means 1 over 2 multiplied by 1 over 2 plus 1, which is 3 over 2, multiplied by 3 over 2 plus 1, which is 5 over 2. And that's 3 steps now. So if you put all of that together, you have 15 over 8. And then, of course, we also saw how Pochhammer symbols can be related with the gamma function, such that a sub n is the same thing as gamma a plus n all over gamma a, like that. So, a very good example of that would be, imagine you have 3 sub 2, or let's say 3 sub 4, that's 3 times 4 times 5 times 6, right? That is 20 times 12. That is 240, I believe. Yeah, this is 12 times 30. Yeah, 12 times 30, that's 360. 20 times 18 rather, or that's 360. Okay, so we say that this 3 sub 4 is the same thing as gamma 3 plus 4 all over gamma 3. That means you have gamma 7 over gamma 3. So gamma 7 is 6 factorial, gamma 3 is 2 factorial. Of course, we know 6 factorial is 720 and 2 factorial is 2. That is 360. So you see the relationship actually works like that. So we have that relationship between Pochhammer symbol and gamma function, and of course, factorial. Then let's go ahead and talk about hypergeometric differential equation. The classical hypergeometric differential equation is x into 1 minus x y prime prime. So it's a second order differential equation plus c minus a plus b plus 1 multiplied by x y prime minus aby equals 0, where a, b, and c are the parameters here. Y of x is the unknown function we are looking for. And this is a second order linear differential equation, like I said already. It is second order because the highest derivative is of order 2, and it is linear because you don't have any power more than 2 for y or any of its derivatives. So you have y on its own multiplied by other things apart from y. So y prime on its own, y prime prime on its own. Then we talk about the singular points. The equation has singular points at x equals 0, x equals 1, and x equals infinity. Okay, so these are regular singular points. These are regular singular points. And we from there we can talk about the Frobenius series solution, which I took care of correctly under the playlist on differential equations. So Frobenius series solution, we assume a power series solution y equals summation from n equals 0 to infinity a sub n x raised power n plus r. And if you substitute into the hypergeometric differential equation, it produces a recurrence relation, and the resulting coefficient generates the hypergeometric series. So this means we differentiate it one time. That'll be y prime equals summation from n equals 1 to infinity, then an into n plus r, x raised by n plus r minus 1. We differentiate the second time again. We have summation from n equals 2 to infinity for a sub n into n plus r into n plus r minus 1, x raised by n plus r minus 2. We substitute all of that into for y prime prime, y prime, and y. And by the time we do all of that, we get so that produces a recurrence relation, and from there we can get the resulting coefficients which generate the hypergeometric series, which is actually a solution to the hypergeometric differential equation. So talking about the recurrence relation now, we have that here. So suppose y is summation from n equals 0 to infinity for a sub n x raised power n, then y prime, so this is the derivative now. So it brings down the power n a sub n x raised by n minus 1. Second derivative now. So this n is equals 1 to infinity here. You now have second derivative n equals to infinity, n into n minus 1, a sub n x raised by n minus 2. So if you substitute into the differential equation, that yields the recurrence formula a sub n plus 1 equals a plus n into b plus n all over c plus n into n plus 1 multiplied by a sub n. And with this now, so for instance, if you have a1, if you need a1, that means n is 0. So that means you have ab all over c multiplied by a naught, ab over c multiplied by a naught. And then once you know what a naught is, you can keep generating the terms like that. So that is what we come to do over here, talking about the hypergeometric series now. So here you have the hypergeometric series. The Gaussian hypergeometric series is then defined by 2 sub 2f sub 1 a b c x. So a b c are the parameters, and that is the same thing as summation from n equals 0 to infinity for a sub n for Pochhammer, b sub n Pochhammer, all over c sub n Pochhammer, and then you have x raised power n factorial, provided that c is not equal to 0, minus 1, or minus 2. So c is not is c is non-zero and it is positive. That's the idea here. So c is not equal to 0 downwards. So c has to be from 1 upwards, basically. So and then we can get the first few terms in that case. So based on this expansion now, so if you get the first 3 terms of this, for instance, when n is equal to 0, we have a sub 0, b sub 0, c sub 0. So all of that will be 1. And then we have x raised by 0, which is 1. N factorial, 1 factorial is also 1. So that's why we have 1 here. So when you take n to be 1 now, so you have a sub 1, b sub 1 over c sub 1. All of that will just be uh just a, right? That'll be a times b over c, and then x raised by 1 is x. 1 factorial is also 1. So the other one was 0 factorial, which was 1 here. So you have the second term. For the third term now, you have a sub 2, b sub 2. That's when n is 2 now. A sub 2, b sub 2, c sub 2. So a sub 2, that's a times a plus 1. B sub 2, that's b times b plus 1. C sub 2, that's c times c plus 1. Then x raised to power 2, that's why you have x squared here. N factorial, that is 2 factorial. And it goes on like that. So these are the first three terms of the hypergeometric series. And then we talk about the radius of convergence. Using the ratio test, we see that the absolute value of u sub n plus 1 over u sub n approaches the absolute value of x. Therefore, we can say that the series converges for x less than 1, absolute value of x less than 1. So at x equals 1, the convergence depends on the parameters at x equals 1. But for absolute value of x less than 1, then the series would converge. Then we have an example here. If you need to evaluate sub 2 f sub 1, 1, 1, 2x, that means a is 1, b is 1, c is 2. So using the definition, we know 1 sub n, that's n factorial. 2 sub n will be n plus 1 factorial, because that will be n. 2 sub n, that's like 2 times. Okay, you do this up to n, right? So 1 sub n is n factorial, 2 sub n is n plus 1 factorial, and so on. Thus, we can say that 2 f sub 2 sub 2 f sub 1 of 1, 1, 2x will now be summation from n equals 0 to infinity for. So you have 1, 1 here. So 1 sub n, that's 1 factorial. 1 sub n again, and that 1 factorial, because this is a sub n, b sub n. So that's 1 sub n, b sub n. So that's n factorial here. And down here, you have c sub n. Because c is 2 now, 2 sub n is n plus 1 factorial. So, and then you have x raised by n over n factorial. And that simplifies to what you then have. N factorial, all over n plus 1 factorial. N plus 1 factorial already is okay, n plus 1. So n factorial cancels n factorial, so that's gone. And n factorial is n times n minus 1. Or better still, you have n factorial up here, and n plus 1 factorial is n plus 1 times n factorial. So n factorial cancels out. So you have x raised by n remaining at the top, n plus 1 remaining down here. And that's a simplified situation. So if you use the logarithm series, we have minus ln into 1 minus x. And that is simply the same thing as summation from n equals 1 to infinity for x raised by n all over n, like this. So in that case, we then obtain that sub 2f sub 1 of 1, 1, 2x will be minus ln 1 minus x all over x, like that. So that's what we get in that case. So for talking about the radius of convergence and for the hypergeometric series. So we move on to Gauss hypergeometric function. So the function sub 2f sub 1 of a comma b semicolon c semicolon x is called the Gauss hypergeometric function. It is a solution of the hypergeometric differential equation, just like we've seen before. And then talking about the fundamental solutions, now we say that one solution near x equals 0 will be y1, which is 2 sub 2f sub 1 of a comma b sub semicolon c semicolon x. So a second independent solution will then be y sub 2, which is x raised by 1 minus c, 2 sub 2f sub 1 into a of a minus c plus 1, b minus c plus 1, and 2 minus c semicolon x, provided that c is not an integer. Then you have Gauss summation formula. So if the real part of c minus a minus b is greater than 0, right? Then we can say that 2 sub 2 f sub 1 of a comma b semicolon c semicolon 1 will be gamma c into gamma c minus a minus b, and then all over gamma c minus a gamma c minus b. I know that all of that is coming because so that now this will have to be c minus 1 factorial, and this will be c minus a minus b minus 1 factorial, and all of that. So take an example. You want to compute sub 2 f sub 1 of half full colon 3 over 2 comma 1. That means a is 1, a is half, b is half, 3 over 2, c is 3 over 2, and x now we're actually evaluating at x equals 1. So using the Gauss summation, we know that to just be gamma 3 over 2, gamma half, all over gamma 1 multiplied by gamma 1. That's using this particular expression now. So C, that's gamma C. That's gamma 3 over 2. C minus A minus B. That is 3 over 2 minus half minus. So that's 3 over 2 minus 1 in short, which is half. And then C minus A, that's half minus 3 over 2 minus half. That'll be 1 each here. So using this particular, so this is the Gauss summation formula being referred to. So using all of this now, we just have gamma 3 over 2 gamma half all over gamma 1 gamma 1. So we know that gamma half is square root of pi. Gamma 3 over 2 is half square root of pi. So everything together then becomes, this is half square root of pi multiplied by square root of pi. That'll be half times root pi. That's half pi. So, and gamma 1 each is 1. So everything is just half of pi, which is pi over 2 in that case, if you have to evaluate this. So with that in place, then, of course, even x is gone. So it should have been x raised power 2 and all that. But we just use the summation formula here. Then we have the Euler integral representation. Euler's integral representation is actually sub 2f sub 1 of a comma b semicolon c semicolon x equals gamma c over gamma b gamma c minus b integral from 0 to 1 t raised per b minus 1 minus t raised per c minus b minus 1 minus x t raised per minus a dt. And that is valid when the real part of c is greater than the real part of b, and all of that is greater than 0. Then we have some transformation formulas. Hypergeometric functions satisfy many transformation identities. For instance, we have the Euler transformation, which is sub 2f sub 1 of a comma b semicolon c semicolon x, which is equal to 1 minus x raised plus c minus a minus b. Then sub 2f sub 1 into c minus a comma c minus b have semicolon c semicolon x. And then we have the Pfaff transformation, which is sub 2 f sub 1 into a comma b semicolon c semicolon x, which is equal to 1 minus x raised per minus a sub 2 f sub 1 into a comma c minus b semicolon c semicolon x all over x minus 1. So these are some transformation formulas as far as hypergeometric functions are concerned. Then we talk about analytic continuation. So a hypergeometric series converges only for the absolute value of x less than 1. So to extend beyond the unit disk, we use analytic continuation. So then we talk about branch points now. The hypergeometric function has branch points at 0, 1, and infinity. When we started, we talked about uh, points of discontinuity. There's a special name it's called, like we saw before. For the first equation, we have singular points. Yeah, they're called singular points. These are the singular points in this case. So the hypergeometric function has branch points at 0, 1, and infinity. And a common branch cut is taken along 1, include 1 and exclude infinity. So within this half closed, half open interval. So we have a common branch cut taken along that path. Then analytic continuation formula then is sub 2f sub 1 into a comma b semicolon c semicolon x equals a sub 2 f sub 1 into a comma b semicolon a plus b minus c plus 1 semicolon 1 minus x plus b into 1 minus x raised by c minus a minus b sub 2 f sub 1 into c minus a c minus b c minus a minus b plus 1 semicolon 1 minus x, where we now say a is gamma c into gamma c minus a minus b all over gamma c minus a over gamma c minus b. And for b now, we have gamma c gamma a plus b minus c all over gamma a multiplied by gamma b down there. Then we go ahead to talk about confluent hypergeometric equation. So the confluent hypergeometric equation is xy prime prime plus c minus xy prime minus ay equals 0. So in this case now, we have, if you compare it with okay, let me just go here and check hypergeometric equation. So can we compare side by side? Okay, maybe let me rush up there and see what is missing. A and B are two. Okay, there's A here, but the equation is now a bit different in that we have, okay, for instance, we have just y prime prime, right? We have just y. Okay, you know what? I'm just going to screenshot this, but I won't be able to paste it there. Okay, let's leave that alone. But I mean, look at what the original hypergeometric equation looks like. We have all these plenty attachments, but when you come to the confluent hypergeometric function, some of those terms are now not available. So here you just have x into y prime prime instead of x into 1 minus x that we had before, plus c minus xy prime. So the whole b thing is gone, minus ay equals 0. So this one has a regular singular point at x equals 0, and it has an irregular singular point at x equals infinity. In case you're wondering about the whole regular and irregular singular points thing, you also want to check the differential equations playlist. I talked about this a lot, especially under series solution. Then we have confluent hypergeometric function, right? So the series solution to the confluent hypergeometric equation is actually sub 1 f sub 1 comma into a semicolon c semicolon x, which is equal to summation from n equals 0 to infinity for comma a sub n x raised to power n comma c sub n n factorial. This is also called the Kummer's function. So the Kummer's function is the series solution to the confluent hypergeometric equation. So we have an example to deal with. You want to compute sub 1 f sub 1 of 1 semicolon 2 semicolon x. That means here that a is 1 and c is 2. So using the definition now, that's the definition of this particular expression. So it means that we have a sub n, right? That's 1 sub n, that's n factorial. So that n factorial automatically cancels this. So we have this x raised by n remaining. And for this, we have 2 sub n. We have 2 sub n because c is n. So 2 sub n is n plus 1 factorial. So it's n plus 1 factorial. So I'm wondering whether one went to. This is a sub n. So a sub n is n factorial. That cancels this. That's 1 sub n. Then 2 sub n is n plus 1 factorial. So where does that go? So we have n. So I think it should be n plus 1 factorial down here actually. So you then have 1 sub 1 f sub 1 of 1 semicolon 2 semicolon x equals summation from n equals 0 to infinity x raised by n over. I think this should be n plus 1 factorial actually. And then this simplifies to e raised by minus x minus 1 all over x. Of course, for e raised power x to appear here, so it means that there must be a factorial thing going on here. So that's why I feel that this n plus 1 should be n plus 1 factorial, actually. So you want to check that to be sure. So we have the Kummer functions. The two standard solutions are first kind, you have m of a comma c comma x, which is equal to 1 sub 1 f sub 1 into a semicolon c semicolon x. And the second kind is u of a comma c comma x, and the Kummer transformation then is sub 1 f sub 1 into a semicolon c semicolon x equals e raised power x sub 1 f sub 1 into c minus a semicolon c semicolon minus x. Then we have the polynomial cases. So when a is equal to minus n, with n a non-negative integer, then the series terminates. Like in this case now, if a is equal to minus n, so in that case the series terminates. So example, if you have 1 sub 1 f sub 1 into minus 2 semicolon 1 semicolon x, then that simply becomes 1 minus 2x plus x squared over 2. So whenever we have a to be equal to minus n, then which with a non-negative, with n being a non-negative integer, then we say that the series will always terminate like that. Then we have the Whittaker equation. So for the Whittaker equation, now Whittaker function satisfies d squared y dx squared plus 1 minus 1 over 4 plus k over x plus 1 over 4 minus m squared over x squared multiplied by y equals 0. And then we have the Whittaker functions. The standard solutions are m sub k comma m of x and w sub k minus comma m of x. They can be written in terms of confluent hypergeometric functions. Okay, then we go ahead to talk about the representation formula now. We have m sub k comma m of x equals e raised to minus x over 2 x raised by m plus 1 all over 2, then sub 1 f sub 1 into m minus k plus half semicolon 2m plus 1 semicolon x. Then we have the generalized hypergeometric functions. So the generalized hypergeometric function is sub p f sub q into a sub 1 all the way to a sub p semicolon b1 all the way to bq semicolon x. And that is defined by sub p f sub q equals summation from n equals 0 to infinity of Pochhammer a1 sub n all the way to Pochhammer a sub p sub n x raised power n over n factorial. Then you have b1 Pochhammer b1 sub n all the way to Pochhammer bq of n, like that. So that's the generalized hypergeometric function. So we then have important special cases like e raised power x. E raised power x is so for e raised power x, p is 0 and q is also 0. That's sub 0 f sub 0 of x, like that. So that will result to e raised power x, because here you know all the b and q are just 0 each. So you have e raised power x left in that case. Then you have that will just be this, so everything here will just be 1. So you just have summation x to the power n by n factorial, which is as good as e raised power x in that case. Then you have the Bessel function, which is j sub nu of x equals x over 2 raised power nu all over gamma nu plus 1, then sub 0 f sub 1 into semicolon nu plus 1 semicolon minus x squared over 4. That's the Bessel function there. And then we have the Gauss hypergeometric function, which is 2 sub 2f sub 1 into a comma b semicolon c semicolon x. Then that brings us to the convergence rules. So for case 1 now, if p, remember this pq from the generalized place, so sub p f sub q. So if p is less than or equal to q, then the series converges to all finite x. Then for case 2, if p is equal to q plus 1, right? Like if p is 1 and q is 2, for instance, the series converges for absolute value of x less than 1. I think that works for this Gauss hypergeometric function, for instance, because p is 2 and q is 1, right? So for case 3 now, if p is greater than q plus 1, then the series diverges except at x equals 0. So these are the 3 convergence rules there. Then we can have some Python implementations. So for Gauss hypergeometric function, so from scipy.special we'll import hype 2f1, that's the Gauss hypergeometric function now. So we can implement that here. So you can just compute it straight here by just putting whatever values you need to put. So I remember the other time we computed this for 0. Half 3 over 2. That's like 0 0.5, 0 0.5. So I'll just copy this now. Okay, I'll copy this and then create a new one. And then I can even do, okay, let me just do this first. I do 0 0.5, then 0 0.5, then 1.5. So for x equals 0 0.5 also. So we have this. What if I want to use SymPy now? Let me try if I can do SymPy here. So I have to import SymPy as SM. Let me call it SM. Then I now declare my variable x is equal to symbol, or I can even do symbols, this. Then I have x is my symbol here. So I just want to have this value raw form in that polynomial format. Okay, something is not right. Name symbol is not defined. Okay. Or what should I have done here? SymPy as SM. X is equal to symbols. Or should I just say symbol here? Oh, okay, I know what's wrong. So it should be the symbols are coming from SM. So they can't come on their own. Yeah, that should be the issue there. Okay. Module SymPy has no attribute symbol. Okay, that should be symbols. All the iterations. Yeah, now we got it. Okay, now the new issue is, oh, these aren't supported for the input types, and the inputs could not be safely coerced. Okay, got it. No worries. So this only works for when you give the particular value of x. So we can go for that then. So we can just, so whatever value of x we need, we have to fix it. So we are not able to do the symbolical stuff, the symbolic computation of hypergeometric. So here we want to do um the Gauss hypergeometric function 112x. So we want to plot it. So it's the same thing we did up here, but we just want to plot that now. So when we plot it, see what that looks like. So we just have this line going up like that, hypergeometric. Then we have the confluent hypergeometric function. So in this case now it's hype 1 sub 1 f sub 1. So not like the 2 sub 2 f sub 1. So we have this going on here, but for x equals 1.5, then we can also have some. Oh, okay. Simple is able to work, except that the expression is different. So in this case now, from SymPy, okay. So from SymPy, we have to import hyper. So from SymPy.abc, we import x. So we don't have the expression to be hyper. So that this is A is 1, B is 1, and C is 2 now. So 1, 1, 2, and then we have all of this. So it is expressed in this form. So I want to see if we can evaluate. Aha, if you substitute, can that work? Okay. Okay. Yeah. So what happens when we have this? Okay, so that's substituting 1.5 into that. Can we evaluate? Eval. Okay. Can we evaluate that? That's what I'm trying to do now. Yeah. So that will give us some. Okay. That's not still working. Okay. Yeah. So let me just leave it the way it is then. So we can get the expression with x in place, or if you want to substitute something for x. So we can just do the substitution also. So if I uncomment this now, I get the one with 1.5. If I comment it, so we just get the expression with x, raw x. So talking about the applications here now, hypergeometric functions appear in quantum mechanics, like we've said already, electromagnetic theory, wave equations, geometry, statistics, mathematical physics, and examples include hydrogen atom wave functions, Legendre functions, Bessel functions, elliptic integrals. Now, we already said it that most of the special functions, like Bessel, Legendre, and all the rest, they're actually special cases of the hypergeometric functions. So we then have the elliptic integral representation. The complete elliptic integral can be written as big K of small k, which is pi over 2 sub 2 f sub 1 into half comma half semicolon 1 semicolon k squared. That's the elliptic integral representation. In summary, then we can say that the cohierarchy is the Gaussian hypergeometric function 2 sub f sub 1, and that then after that we have the uh the what's the special name for this now? Confluent hypergeometric function. That's sub 1, f sub 1, and that leads to Whittaker functions, and then that leads to the generalized format. So the main ideas are as follows. We have hypergeometric differential equations, and from there we have power series solutions to them, and then we get transformation identities. We have analytic continuation, we have confluent limits, and we have generalized special functions. So hypergeometric theory unifies a vast number of special functions into one coherent framework. So that takes us to the practice problems. And of the 20 practice problems, you're going to solve two as usual. So we see that the first one says to derive the recurrence relation for the coefficients of the series solution, x into 1 minus x, y prime prime plus all of that using the Frobenius method. I mean, I dealt with the Frobenius method a lot under differential equations playlist. You want to check that out. Then compute the first 5 non-zero terms of this. Show that this, I think we are going to solve 3 and 14. So this is going to be dealt with. So I want to show that sub 2f sub 1 into a of a comma b sub semicolon b semicolon x is simply the same thing as 1 minus x raised power minus a by simplifying the series solution. Then so we'll be taking care of 3. Then I'll just show the other question. So this is you have question 4 to 7 here, question 4 to 7, and then you have 8 to 12 here, 8 to 12. Then you have 13. You have question 13 to say maybe 13 to 16, that can be seen clearly. 13 to 16. So we'll be taking care of 14 also. So problem 3 and problem 14, that's what we're solving here. Then you have 15 to 18 and then the rest. So we can say 18 to 20 like this. So let's go ahead and take care of these two problems. So we have problems 3 and 14. So let's take problem 3 for starters. Problem 3. So you want to show that sub 2f sub 1 of a comma b semicolon b semicolon x is the same thing as 1 minus x raised to power minus a. That's what we are required to show. Okay, so the solution, okay, by simplifying the series solution, right? By simplifying the series solution. Okay, so let's go for that. So first, for the solution now, start we start from the definition of the Gauss Gauss hypergeometric function, and that is sub 2f sub 1 of a b semicolon b semicolon x. This can be defined as a summation from n equals 0 to infinity for a sub n, that's Pochhammer a sub n, Pochhammer b sub n, all over Pochhammer b sub n, because now b and c are equal, and then we have x raised to power n all over n factorial. So we have that in place. Then we can go ahead to say, since Pochhammer b sub n appears in both numerator and denominator, they simply cancel, right? They cancel. So canceling means, I mean, this and this will go because they are the same. So if we are to rewrite this expression now, it means we have sub 2f sub 1 into a comma b semicolon x. That will simply be summation from n equals 0 to infinity, comma a sub n, x raised by n, all over n factorial. So with that in place now, we can then see, so what can we do with a sub n? Let's see that. A sub n would be gamma a plus n all over gamma a. Okay, so this expression itself, right? We can recall. So now recall the okay, the question itself says to do that by simplifying the series solution. Okay, let's just go ahead and do the simplification as much as we can. So here we have summation from n equals 0 to infinity, comma a sub n, x raised by n all over n factorial. So we can say this is summation from n equals 0 to infinity. Comma a sub n is still the same thing as gamma a plus n all over gamma a, right? And this is x raised by n all over n factorial. Okay, so that means we have summation from n equals 0 to infinity, and then here that will be a plus n minus 1 factorial up here all over a minus 1 factorial. Then we have x raised by n all over n plus 1 factorial. So we have to move smartly here. 1 minus x. Okay, so what exactly can we do here? This is a plus 1. Mm, okay. So if we check, okay, if we check, we can check to see that 1 minus x raised power minus a is as good as summation from n equals 0 to infinity for Pochhammer a sub n over n factorial x raised power n. So this is a standard expression. So, so if we expand this, we're going to get exactly this. So with that in place, then we can say therefore 2 sub 2 sub f a comma b semicolon b semicolon x can then be said to be 1 minus x raised power minus a, like that. So you can just expand this and see that it's related with this. So this proves which then proves the identity, which proves the identity. Then we go for problem 14. Problem 14. So it says to evaluate the terminating series, sub 2f sub 1 in of minus 3 to semicolon 1 semicolon x explicitly explicitly as a polynomial. Okay, so in that case, then we move on to say that we start with the definition. Start with the definition. 2 sub 2 sub 2f sub 1 of minus 3 comma 2 semicolon 1 semicolon x is summation from n equals 0 to infinity minus 3 sub n 2 sub n all over 1 sub n x raised power n all over n factorial. So because because the parameter because the parameter that's a now is minus 3, so it means that the series terminates after n equals 3, because we have this parameter to be minus 3 here. So thus we then have sub 2 f sub 1 minus 3 to full colon 1, I mean semicolon 1 semicolon x equals summation from n equals 0 to 3. So it just stops at 3 because of that minus. So we have minus 3 sub n, 2 sub n, all over 1 sub n. That's Pochhammer, x raised power n over n factorial. So we can compute term by term. Do we have to compute term by term? We can do everything together, right? We can do everything together. So let's just go together so we don't lose track of this. So I just keep on with this now. So our work is cut out for us here. We just have to do this from n equals 0 to 3. So we're going to have 4 terms. So first term we have minus 3 sub 0, um minus 3 sub 0, 2 sub 0, all over 1 sub 0, then x raised by 0 over 0 factorial. That's the first term. Second term, minus 3 sub 1, 2 sub 1, all over 1 sub 1, then x raised by 1 over 1 factorial. That's the second term. The third term is now minus 3 sub 2, then 2 sub 2 over 1 sub 2, x raised by 2 over 2 factorial. And lastly, we have minus 3 sub 3, minus 3 sub 3 into 2 sub 3 all over 1 sub 3, then x raised to power 3 over 3 factorial, and so on and so on and so forth. Oh, yeah, no, it terminates at 3, yeah? So there's no continuation to that. So then we can tidy this up to say that this is 2 sub 2 sub f, sub 2f sub 1, right? Of minus 3, 2, minus 3 comma 2, semicolon 1, semicolon x. We now have to be, so we try to tidy this up as much as possible. So minus 3 sub 0, that is 1. 2 sub 0 is also 1. 1 sub 0 is 1. X raised by 0 is 1. 0 factorial is 1. So everything here is 1 in short. Plus then minus 3 sub 1. So that would simply be minus 3 sub 1. That will be minus 3. Then 2 sub 1 is also 2. Then 1, okay, this is 1 sub 1. That's also 1 here. Then x over 1. Then for this now, we have plus minus 3 sub 2. Minus 3 sub 2 will just be minus 3 times minus 2. Then 2 sub 2, that's 2 times 3, all over 1 sub 2, that's 1 times 2. Then x squared, that's x squared. 2 factorial is still 2. Then minus 3 sub 3, then minus 3 sub 3, that'll be minus 3 times minus 2 times minus, oh, yeah, yes, because we are increasing the powers. Yes. So, yeah. So minus 3 times minus 2 times minus 1, all over, multiplied by 2 times 3 times 4 over 1 times 2 times 3. Then we have x raised to power 3 as x raised to power 3 all over 6. So we can tidy this up now. So we have sub 2f sub 1 minus 3 to semicolon 1 semicolon x, and that will be equal to, all of this is 1 here. Then coming here, we have minus 6x, because this is 1 down here. Then for these 2 now, so this 2 cancels this 2 cancels, so 2 of the 2's. So this 2 cancels this 2 cancels this. So minus and minus. Okay, I think we need to be careful so we don't mix things up. Okay, so I'll just go gradually still. This is minus 3 times minus 2, that's 6 times 6, 6 times 6, all over, let me leave this alone. So this is 2 times 2 down here. Then we have x squared. This is 1 times 2, 2, then this 2. Then when we come here now, we have minus, minus, minus. So all that should be like minus 3 times 2 times 1. Minus 3 times minus 2 times minus 1, that's minus 6. Multiplied by 2 times 3, 6 times 4, that's 24. All over 1 times 2 times 3, that's 6 times 6 here. Then we have x raised to power 3. And that terminates. Then we then have sub 2f1, sub 2f sub 1 that of minus 3 to semicolon 1 semicolon x. That is 1 minus 6x. Then this is 36. 4 here, 4 in 36, that's 9. So that's plus 9x squared. Then here, 6 cancels 6. 6 here is 1, 6 here is 4. That's minus 4x cubed. And that's all we have. So this is the required polynomial now. So 2 sub 2f sub 1 of minus 3 to semicolon 1 semicolon x is 4 minus 6x plus 9x squared minus 4x cubed. That is what we need. That is the required polynomial there. So with this, we come to the end of this interesting video on hypergeometric theory. Okay, again, I flashed the problems. So we have 1 to 3, then 4 to 7. Yeah, 4 to 7. Then we have 8 to 11. 8 to 11. We have 12 to 16. Then we have, okay, 16 to 17 to 19. Okay, then I just shift 17 upwards and we have 18 to 20. So with that, we come to the end of this interesting video on hypergeometric theory. Okay, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Um, if you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, of course, you want to go ahead and do that right away. And you should also click on the you can also hit the bell so that you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges that you find out as you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.